Okay, so we're going to look today at resistors in parallel. So resistors in series are really easy to calculate, and it's almost not worth uh, looking at it because it's just so straightforward. So as usual, we draw a circuit like that. I'm just going to do a simple series circuit to start with. So that's a power source, that's a resistor, zigzag there. So if this one were 1 ohm and this one were 2, then you simply add the two of them. So the resistance total, which I'm going to abbreviate to just RT in the next line, is 1 plus 2. So we get the total resistance is 3 ohms. Now, got to watch out because the last video I did, I kept dropping my voice and it became really hard to hear me. All right, okay, so what about a parallel circuit? Well, that is not so simple, and there is a reason for it. It's really hard to spell parallel as well. So we do the same thing, we just draw a square or a rectangle. All right, put a power source in. It's like a little, can you see that against my shirt? There you go, against my shirt, there it is. There's the power there. Okay, so now I've got the 1 ohm resistor here, and I've got the 2 ohm resistor here. And I reckon I'm going to run out of room over here. So I think I'm going to have to rub that off. 2 ohms. So I've got a very fancy rag down here. So I'm just going to get rid of that. All right, so this is the problem. When I've got the series circuit, the current flows around there and it has to flow through everything. So it gets slowed down by this one and then slowed down by that one. In the parallel circuit below, what the situation, oh, that is off the screen. That is so annoying. I can't believe it. Okay, I'm going to adjust the computer so it's back on the screen. So the problem is the current, the flow of electricity, the flow of electrons has a choice. And because it can go through there or through there, this actually lowers the overall resistance. Okay? So we're going to call this, we need to label these because we're going to need them as specific values in a minute. And the way that we do this is we say 1 over the total resistance is equal to 1 over the first resistor and 1 over the second resistor. And that just goes on forever. You can add 100 resistors and do it this way. Not that you do it, but anyway. All right, so the calculation is actually fairly simple. So I need to stand here so you can see it. All right, so we simply put in our resistor values. Resistor 1 is 1 and resistor 2 is a half. And then we add those together. So that becomes 3 over 2. If you want to do the whole thing, then we say that's equal to 2 over 2 plus 1 over 2. So that's 3 over 2. And then that is 1 over the resistor total. So to get the answer, I need to flip both of those. Okay, invert this, and I get I just get RT, and on this, I get 2 on top, 3 on the bottom. And we don't usually give resistor values as fractions. So we would probably say for our final answer, which you can't see because things just the wrong way around. Okay, now what am I going to do? I'll rub it off and move it slightly up the board so you can see it. It's going to be so much better next time. Okay. And now you can see that. Good. So that equals 2 over 3. Now it's still almost off the board. 2 over 3, that looks dreadful. Okay, and so the total resistance equals, we convert that into a decimal and we get 0.67. Am I still on the screen? Oh, just. And that is my final answer. Now, does that make sense? Well, I have a 1 ohm resistor here, so my total resistance should be less than 1 ohm because the current can go down here. I've got a choice, maybe I could go down there. Now, of course, that's not how current works. But that's how we imagine it happening. And so the overall resistance of this whole arrangement is 0.67.